Hello there, it's Paul Watts here from High Flying Physics, supporting students wanting to get top grades at A-level physics. This is a classic question on equilibrium. I've chosen it because students often have difficulty when it comes to moments, particularly when it comes to working out perpendicular distances. Let's see if we can help sort this out. A little bit of theory recapping first of all. Conditions for equilibrium, very common starter to a question. Quite often we'll have to state the conditions required for equilibrium. There are two conditions that must be true for a system to be in equilibrium. First of all, there's got to be no net force acting in any particular direction. So the forces acting up the slope must equal the forces acting down the slope. The forces acting vertically must be equal, and the forces acting horizontally must also balance. So, and the second condition is that there's no net turning effect. So in other words, the sum of the clockwise moments are equal to the sum of the anti-clockwise moments. Another quick reminder, which you'll all know from GCSE, but I'm going to say it anyway just in case. Calculating moments. To calculate a moment, we say the moment of a force about a point is equal to the force times the perpendicular distance from the force to that point. Now, the perpendicular distance is an interesting one, and sometimes students get in a little bit of a muddle with it. At GCSE, you would have been very familiar with this sort of problem, where we've got a force which is acting in a perpendicular direction from a distance d and the pivot point at O. And you all know the moment of F about O is force times the distance. Fairly straightforward. If we take a situation which is less straightforward, and this time we've got a force which is not acting in a perpendicular direction. It's acting at theta. In this situation, we extend the line of the force. We draw a line from the pivot point to the line of the force. The perpendicular distance is the line from O to the line of the force that cuts the line of the force at right angles. That, in green, is the perpendicular distance. The perpendicular distance is equal to d sine theta. So the moment of the force about point O is equal to f d sine theta. Now there's an alternative way of working this out. Rather than trying to work out the perpendicular distance, we can actually work out the perpendicular component of the force F instead. So there's our original situation, and we draw on the perpendicular component by using simple trigonometry. Hopefully you can all see that the perpendicular component of that force is equal to f sine theta. So we can say the moment of the force about O is f times d sine theta, which if you compare with the situation above is exactly the same. Okay, let's use that then to have a go at a question. It's a classic question to do with a ladder leaning against a wall. So in the question we've got our ladder, and it's a uniform ladder, and it's got a mass of 85 kilograms. So because it's uniform, the weight is going to act in the middle of the ladder. The length of the ladder is 4.2 meters, and it's resting against a smooth wall and on rough ground at an angle of 65 degrees to the horizontal. And you've got to find the reaction force at the wall. So there's the reaction force at the wall. Again, there's no friction at the wall because we're told the wall is smooth. Part B, work out the reaction force on the ground on the ladder. So there's our reaction force, and if the ground couldn't provide that reaction force, then the ladder would just sink into the ground. And we were told that the ground is rough, so part C, we've got to find the frictional force on the ladder, and there it is. So let's do part A, the reaction force at the wall. The point here is we're going to solve this by taking moments. We can obviously take moments about any point along that ladder. It's always a good idea to identify unknown forces and take moments about that point, because we know that the moments from the unknown forces at that point are going to be zero. So let's take, let's say the base of the ladder, let's call that point A. So we can say clockwise moments about A are equal the anti-clockwise moments about A. So choosing our the force which is making this ladder turn in a clockwise motion, that is force N. We need to find the perpendicular distance from point A to that force N. Just as we did in the previous slide, we extend out the line of the force. We draw a line from A to the line of the force, where it cuts the line of the force at right angles. So that is the perpendicular distance that we're interested in. So there we have it, perpendicular distance. The angle from the ladder to the force N is obviously 65 degrees. Therefore, we got a right angle triangle there. We got the hypotenuse as 4.2. So we can say the perpendicular distance from A to force N is equal to 4.2 sine 65, which is equal to 3.8 meters. The other force that we're going to be interested in is the force which is making it turn in an anti-clockwise direction. And that force is the weight. And so our first job then is to work out the perpendicular distance to that force. So again, we extend the line of the force. There it is. And we're interested then in the distance which from A to the line of the force that cuts to the line of the force at right angles. There's our perpendicular distance. And we can work that out by saying 2.1 cos 65. The 2.1 is half the length of the ladder. We can say that the perpendicular distance is 2.1 cos 65, which comes out to be 0.89 meters. So we can say that the clockwise moment is equal to n times the perpendicular distance, which is 3.8, is equal to w times the perpendicular distance at the point A, which we just worked out is 0.89, and then the rest is a simple bit of mathematics, and n comes out to be 195. Okay, so part B then. We've got to find out the reaction force of the ground on the ladder, R. One of the other conditions for equilibrium, remember, is that forces acting in any particular direction will balance. So if we take the forces vertically, there are only two forces acting vertically. There's R and there's W. The forces acting upwards are equal to the sum of the forces acting downwards. The forces acting upwards is R. The total forces acting downwards is W. So we can simply say that R is equal to 85G, which is equal to 834 newtons. Part C, the frictional force on the ladder. Again, the same thing applies. The ladder's in equilibrium, so we can say all the forces acting to the left are equal to all the forces acting to the right. The forces acting to the left is a frictional force F, and that's going to equal the normal reaction force at the top of the ladder, N, and we've already worked out that is 195 newtons. There we go. I hope you found that useful, and we'll see you soon. Thanks. Bye.